Sedimentary rocks are fascinating because they witnessed the past history of the Earth. Their study should unveil mysteries about their formation and the history of living species. The principal features of sedimentary rocks include distinct stratas of relatively homogeneous material. Intermittent settling over very long periods of time figure among possible explanations of stratification. Internally, sedimentary rocks display microscale stratification or lamination of relatively coarse and fine particles. Because sedimentary rocks form from settling of particles underwater, it is instructive to study fundamental sedimentation patterns in the hydraulics laboratory. A mixture resulting from equal weights of coarse sands in black and fine sands in white is tested in the laboratory.
Consider the motion of a sphere rolling on a horizontal surface. The radius of the sphere is r, the mass is m, the angular velocity omega, and the translation velocity v is equal to omega times r. The moment of inertia of the sphere is equal to 2/5 of the product of the mass m and the square of the radius. The kinetic energy of the motion is given by the following formula. E is equal to 7/10 of the product of the mass times the square of the velocity. This formula shows that at a given velocity, the kinetic energy of a sphere increases with the mass. It shows that coarse particles have a higher kinetic energy than finer particles.
This example illustrates that rolling coarse particles have more kinetic energy than small particles. The mobility of coarse particles in front of obstacles or surface perturbation therefore increases.
Consider a homogeneous mixture of coarse particles in black and small particles in between. When we set this mixture into motion, the small particles, which have a lower kinetic energy, fall between the coarse particles and deposit on the bottom of the moving layer. The coarse particles with higher kinetic energy roll on top of the fine bed of fine particles.
Particle segregation occurs under lateral motion of a mixture. Coarse black particles roll on top of fine particles when they have the same specific gravity. Submerged particles under hydraulic shear stress also display the same particle segregation characteristics. The fundamental question about lamination is the following. Does nature produce repetitive segregation under a continuous supply of sediment? First, the submerged conditions are examined. The turbulent fluid motion surrounding the particles led scientists to believe that lamination was caused by periodic cycles of turbulence. When the same experiment is carried out in the air, the settling cone displays all the features of lamination through repetitive segregation. Moreover, the laminae thickness increases with the feeding rate of the sediment mixture. It should be noted that laminae form in the direction of motion, here at an angle exceeding 30 degrees. Given the absolute vacuum is at minus 29.92 inches of mercury, the hypothesis of turbulence is tested near complete vacuum at minus 22 inches of mercury. Lamination develops without the presence of a surrounding fluid. Lamination therefore depends on the mechanical interaction between particles of different sizes, different shapes, and different densities. Under submerged conditions, lamination also occurs during gradual aggradation of the bed under plain bed conditions. Here's the same lamination sequence in accelerated motion. Large-scale experiments on stratification were carried out at the Hydraulics Laboratory of the Colorado State University Engineering Research Center. For the experiments, a 4-foot wide flume measuring 60 foot long recirculates 1,000 cubic feet of water and 8 tons of a sand mixture. This flume provides a continuous supply of coarse and fine sand particles under steady discharge conditions.
Consider a typical delta sketched on the board. At the initial time T1, the delta is comprised of 3 parts: the top set, the foreset, and the bottom set slope at initial time T1. Over time, the coarse particles rolling on the bed slide down the foreset slope of the delta and accumulate as the delta progresses in the downstream direction. Finer particles rolling on the bed settle and form a layer of primarily fine particles. The particles in suspension are carried through and deposit on the bottom set slope of the delta. After a certain time interval, we get a second bed profile at time T2. The sediments accumulated on the bed from time T1 to T2 define what is called a layer of sediment. A layer of sediment is the accumulation of sediment between the initial time T1 and the subsequent time T2.